So welcome back. Happy Monday. Indeed, right? Yes. Did you all have a good weekend? Yeah, as good as it's going to get? Yes. See, this is part of the reason why your homeworks are due on Friday. That's my hope that if you don't have a good weekend, it's not my fault. That way, in theory, you finish your homework and you finish whatever else you're working on and you get to have an actual break. I wish that for all of you. How you spend your break, of course, is up to you. This weekend, I spent about 2 hours cleaning the house just because I needed a win. Do you ever get that way? It's like you're frustrated with something and it's like, my sink was dirty and now it's clean, I win. It's doable. It's yard work is like that for me. It's like, the lawn is mowed, I win, you know. Until 5 days later when I have to do it again, but you know, it's the little joys in life. So most of you, I think, have finished the homework, but I did want to go over it because there was quite a bit of heterogeneity in how folks did with the drop-down section, so I thought it might be useful to go over that as well as some of the computational questions. So I've got one pulled up here. Let's try and make this a little bit bigger. So section 1, I think, went relatively well. The key idea here is emphasizing that both the outcome and age as a predictor have some portion of between variance. So then the idea that we have a separate age effect for that between variance than from the within variance. So I think that went mostly okay. Whenever you are testing if an intraclass correlation is greater than 0, that's degrees of freedom 1, because all you're adding is a random intercept. SAS and Stata both do this for you by default. On your output, there is a null model likelihood ratio test that tests your current model against one that has an empty G matrix, meaning takes out the random intercept and compares it to the model likelihood without it. So in this instance, you don't have to do any special model fit comparisons. It should show up on your output by default. And let's see here, then we added some fixed effects. So we added a fixed linear age and fixed quadratic age, looked at pseudo R-square and total R-square for those things. So then we get down to the interpretation here, and the general rate of change was an accelerating positive trajectory. So girls had more increases in problems in later ages than earlier ages, according to the model here. And I tried to be a little tricky, and I caught a couple of you on this one here. So the interpretation of the fixed quadratic effective age indicated that the rate of linear change was significantly more positive, is what most of you would have found, and that is by twice the coefficient per year. So you need the per year because that's the x that the coefficient is multiplying. So twice the quadratic is how the linear rate of change changes per unit time, and unit time in my story here is per year. So we're talking about the next pseudo R-square for the residual variance. Residual variance is level 1. Level 1 is within person, so that's why it's the longitudinal within person effects of age. All of the other combinations were either logically inconsistent, things like cross-sectional within person or between person longitudinal. The only other option that would have been plausible is between person cross-sectional, but that doesn't apply to residual variance. That would have applied to random intercept variance. We added a random linear slope and got a significantly better fitting model, degrees of freedom 2, because whenever you start with a random intercept and you add a random slope, you're adding the slope's variance plus its covariance with the intercept that is already there. So that then indicated significant individual variability in linear change. So adding random things mean people need their own. Then random quadratic resulted in a non-significant improvement. So whenever you add something, it's either better or not better. If it's non-significant, that means not better. Degrees of freedom equals 3, and this is the thing that I screwed up when I built the answer key. I copied and pasted 2 from the previous question instead of 3. So it should be the quadratic slope variance plus its covariance with the random linear slope and the intercept. Side note, in SAS, If you're ever in a situation where you're adding a random slope and SAS thinks it's exactly 0, like you get 0 for the estimate and dots where the other numbers should be, it doesn't count that degree of freedom. So if you use my fit test macro, you may get an incorrect degrees of freedom because it doesn't count the thing that it couldn't estimate. I think it should count because you tried to estimate it. So that's why I'm sticking with 3 here. So the fact that this random quadratic model was not an improvement means that there is non-significant individual variability in quadratic change. Okay, with me so far? All right, section 3. So this is the point at which we added age cohort, the idea of adding in a contextual effect. We're saying that it matters when you were 16, when you were 14, that the trends that you would expect as a function of age are in part moderated by which type of kid you are, when were you born, and what are the age trajectories look like for each of those cohorts of kids. And all of you should have found that the cohort interaction with quadratic time was non-significant, and also at this point the fixed quadratic effect of age became non-significant. So in earlier permutations of this homework, I had folks make graphs. I haven't figured out a way to make a graph part of the online homework system, so I didn't make you do that. But the key idea here is that that acceleration that you found initially was a fluke. It was due to an unmodeled cohort effect in which the earlier born cohorts have a more positive linear slope. So if you don't put in cohort, it looks like there's an acceleration, but it's because you have different girls with different linear trajectories that start at different places overall. So the model simplifies at this point to have just a linear effective age, an effective cohort on the intercept, and an effective cohort moderating linear age. And I did that on purpose, believe it or not, to try and be nice, because I thought that throwing in quadratics into your final model would be too much. As it was, keeping age and age cohorts separate and their separate centering points, I think that is enough of a level of difficulty for a first pass at this type of data. So we have then these questions, and because I answered these same questions for folks in office hours over email, I wanted to go over them and make sure that everybody is crystal clear on how to get these answers. So the model at this point has only those 3 fixed effects. Age 16, which is time varying age centered at 16. Age cohort, which is time invariant cohort centered at 14, and their interaction. So questions 28, 29, and 30, or actually no, 28 and 29, both wanted you to do predicted age change. So age change is this term right here. In these types of designs, things that used to be semantic distinctions start to become more important. So if I say age change, that's different than age differences. The term age differences refers to a cross-sectional effect of age, whereas age change is longitudinal. So cohort effects are differences because they're differences between different people. Age change is when you're watching the same person get older and you can see what happens to them. So age change in problems, that's the thing that we want. So when I write my estimate statement, I start then with the thing that, no, I get the thing that I want here. And because it is the root, it is the thing that I want, what does it get? 1. Doesn't matter what the rest of the sentence says, it starts with a 1. Because at a minimum, you need that fixed effect of age 16 to get you the predicted age change for anybody. At a minimum, that's all you need if everything else were to zero out. Now the rule for estimate statements, given that this is the thing I'm trying to estimate, the root, the only other term that belongs in here is the interaction with cohort, because age 16 must be present in every term in the estimate statement. And if I want the effective age for somebody who started at 12, then I put a -2 here, because that is when age cohort 14 would be 12. So age 16 gets a 1, age cohort gets the value for which the cohort is 4, which is 12 here, and so that's a -2. So most common mistake, other than centering things incorrectly and putting, say, -4 here, confusing it with 16 versus 14, was that folks really wanted to put in the main effective cohort. But the main effective cohort moderates the intercept. It does not moderate the age slope, so it doesn't go there. And if we do the same thing then for people who started the study at 16, do I change this first term? No. Yes, thank you for being emphatic. It's better to be wrong than vague, right? Do I change this number? Yes. What do I change it to? 2. Yes. Clean sinks for everyone. You're winning. Now, the other ones are going the other way for the interaction. Every two-way interaction can be interpreted 2 different ways. Both are equally correct. The way that you talk about in a paper depends on what your story is going to be. So the first 2 estimate statements are designed to illustrate what do age trajectories look like for different groups of girls. So cohort is the moderator, but the other way to think about it is what is the effective cohort and how does it evidence itself differently at different ages. So then cohort is the predictor, time varying age is the moderator. So predicted difference in problems per year of age cohort. That is one thing. That is the effective age cohort. Predicted difference in problems per year because this isn't a per year variable. So that gets the 1. That's the thing I want to estimate. The only other thing that I need then is how that effective age cohort would be different at different time varying ages. So if I wanted the effect of age cohort at age 12, what goes in this variable right here? -4. And it's not -2 this time because age cohort gets the 1. So we're filling in the value for time varying age that we want. And if it's at 12, it's a -4. Likewise, what is it here? 0. Do I even need to write that estimate statement? No. How can I tell? Just by looking at the pattern here. Not a linear combination, right? There's only one term that gets a 1. That means that's already on your output somewhere. That is what's given by the model directly in the solution for fixed effects. And last but not least, this one will be +4. Ta-da! What was interesting to me is that homework 1, with its 93 questions and its 4-way interaction, gave people less fits than this. Isn't that interesting? That's my qualitative assessment of your quantitative performance. I know, right? By the way, this term age cohort, if you ever use that term in a manuscript, make sure you define it as continuous, because that word cohort, people automatically think group. So just as a heads up. I haven't come up with another way to describe what that variable means other than age cohort. But yes, it's hella confusing when you have age and age cohort in the same model. But the big picture, why do we have to have both? Because age has both. Age has cross-sectional variance differences in age at the beginning of the study. That's cohort. Age has longitudinal variance differences in age as the girls get older. And so they both belong in there. And KU Information Technology has decided it's going to do something without my permission. How nice! In the middle of my lecture. I love it. Well, the words under that one? Yes. Maybe. Oh, okay. Well, we'll move that there. We shall look at the words, because words are important.
I was confused about the one in the quiz. Significantly greater increase across age for girls born sooner.
So born sooner means that they are older when they started the study. So if we look at the direction of the coefficients, everybody should have had a negative effect of age cohort on the intercept, but a positive effect of age cohort on the slope. So at a given age, at the centering point at 16, the people who were born sooner, the people who started the study older, they were lower, but they had a trajectory that was more positive, was steeper.
Born sooner too.
Older cohorts. Meaning that when the study started, they were already older?
Oh, it's like born earlier.
Yes. That's what I meant? Okay, yeah, sorry. I will, I'll...
It seems like closer to the time right now.
Oh, okay, I'll give you that. Did anyone else think
It was the 12-year-olds who
born sooner to now?
Yeah.
Okay, did anyone else think that? Okay, I'll take it. That, thank you for speaking up. I need to make sure that the words are sufficiently clear, and that is a reasonable alternative explanation. So I will fix it. I will give you credit for that if you thought that's what sooner meant. See how reasonable I am? So which ones would that be here? Be 59, and does it affect this one here? I don't think so, because this is just saying the effective cohort. And if you've got these numbers right, you should see that -3 to -1 to 1 means less negative. So, okay, 59, I will take that one and fix it. All right, any other questions before I shut this one down? Homework 3 is not up yet, so you have another brief shining moment where there's no homeworks outstanding. But you do have a quiz you can work on, so just in case you were afraid that you had to actually do something you didn't want to do, here's something you can do instead. Yes. All right. So I have some new material today. It starts off with some somewhat old material, but it's, I think, necessary to remind you so that the new stuff makes sense. So, model assumptions. Before I dive into that, can I tell you a quick story? Just to give you a little background on my philosophy on checking model assumptions and whatnot. Just a couple different stories actually today. So when I was a postdoc, I was at Penn State University, and I did some sort of consulting freelance work with the stats department there because they had an applied master's program, basically where it was a 2-year program. They trained people to be statistical consultants. Seems like a great, data science, by the way, that's what that's called now. That's the new buzzword. And they had a consulting class where they matched up people from across campus with the students, and their supervisors would help them provide advice to do analyses. And in this class, they wanted some pretend clients to come in to start getting them used to asking the right kinds of questions. So I agreed to be a pretend client. And I came in and I said, okay, I have data. And they're like, what do you want to ask her? And one said, what's the outcome? And in my story in my head, I said, response time. It's kind of like playing 20 questions, like how long does it take before I get enough information to do your analysis? Do you know what the next question was? Does it meet the assumptions of the analysis? That was question 2 from someone. And I told them, if I knew what that question meant or how to answer it, I would not be here asking for your help. But it highlights the difference, I think, in how social scientists who take applied statistics classes like this one get trained differently than folks who take like hardcore capital S statistics classes, right? Assumptions get taught much harder, much sooner, and much more rigorously in those types of classes. So for some folks, they would be like, why are you just now getting to this? Other people like me, it's like, well, I never know what the right answer is, but I do know that I've got to analyze these data and make a decision, right? So if it doesn't meet the assumptions of the analysis, I've got to figure it out. I've got to make it work somehow. And the repertoire of ways to make it work when it doesn't meet the assumptions should involve changing the model, not the data. So that's what I'm going to use this lecture as a jumping off point, really, for the rest of the semester. How do we change the model when we need something more than what we currently have? The reason that we have the assumptions that we have goes all the way back to estimation, though. And so that's why I threw in a few slides from chapter 5 here, just to give you a brief review as to what that process entails. So two sides of the model, folks, right? Fixed effects in the model for the means, and random effects and residuals in the model for the variance. So in thinking about how to find numbers, and therefore if our model assumptions are correct, we have to worry about each of the sides. The random effects side in the models that we're talking about, the term general applies to all these models. Do you remember what that means? General versus generalized? Remember those terms? What does "ized" mean? Anybody remember? Outcome is not normal, is "ized." Generalized models are things like logistic regression or count regression, or IRT models in the world of latent trait analyses, factor analyses. Whereas the term general means the residuals are plausibly normal after accounting for the random effects and the residuals. So everything that we've done so far is general models. General meaning normal residuals. And in that case, the way that estimation works is that it's first trying to figure out the parameters for the model for the variance, and it then uses those to calculate the fixed effects. And I don't say estimate, I say calculate, because there literally is a formula. So in thinking about estimation, all of the concern really is in the model for the variance. So the process of estimation then, we've talked about maximum likelihood as one way of doing estimation. MCMC Bayesian models is another way. It's the exact same model, but a different way of getting the answers that involves also incorporating a prior distribution for each of the parameters. But we still, in the process of using Bayesian estimation, have this likelihood function, and this thing is the root of why we make the assumptions that we do. So let me give you a picture I stole from Wikipedia here. This is the univariate normal distribution. This is the thing that you get taught first in every stats class in a stat department or in psychology or other social sciences. Ironically, it's the one that has the most complicated formula, I think, in terms of a probability distribution. It's the scariest looking, but it's right here. So those curves are generated by this thing. This thing, let's go through it here. Let's see, that's a 2. We know what that is, right? Pi, what's pi? 3.141. Say, anybody want to show off and give me some more? I only know 3.141. Right. 5.9's next one. Yeah. Any more? No. 5.9. Okay. I'm going to accept that you're correct. I don't know these things. But yes. Then we have a square root or root. If you're from the Midwest, Duke, we take a survey on that. Is it root or root? It's root. Votes for root. Votes for root, square root. You go up on the roof and eat your root beer. It's root, right? It rolls right off the tongue. Maybe it's just me. But the only thing in here that we need to know is how far off you are from what's predicted for you, that y hat. That's where your fixed effects come in, and residual variance. So each person's predicted value has some kind of distribution, and everybody shares the residual variance. And the process then of finding these fixed effects and these residual variances is trying to make the data as tall as possible. So for each person's real data point, we can calculate how likely it is to observe it if we have this particular set of model parameters. Univariate normal is what we use if we have one outcome per person. If you have multiple outcomes per person, it's harder to picture, But if you think of 2 outcomes, then it's like a big taco, like a multivariate normal distribution. If you have a strong correlation, it gets like a real skinny taco. Otherwise, it's like a big sphere if you don't. But that then takes that univariate normal formula that we just saw, and it changes it to make it multivariate. So when we're talking about longitudinal data, for instance, or any kind of nested data in which a sampling unit has multiple outcomes collected for it, then that multivariate normal formula is what we use if we've selected a general mixed model. So we still have our pi in here. That sigma squared E, which used to be just residual variance all in one pile, that goes to my letter here, V. Remember what V is? V for victory? How do I get a V matrix? Yeah, G plus. You got to do the air quotes though, right? G and R combined because you can't add them directly together. Remember what's in G? Level 2 or 1? 2. So what's in G? Random stuff or residual stuff? Random stuff. Random intercept and slope variances and their covariances, that's G. What's in R then? Residual variances and covariances. When you put them back together again, you get this thing V. So given current guesses for what all of those things are, random intercept variance, random slope variances, however many you have, covariances, and residual variance in whatever pattern that you're building this V for each person, note that V has an I subscript. Everybody gets their own custom V matrix based on whichever data occasions they have, based on whichever values for the predictors that have random slopes they have. That's how we can handle unbalanced data, right? Because each person gets their own V, and that's how we can handle missing data, because everybody's V can be of a different dimension. You can have a 3 by 3 if you only have 3 occasions, or a 4 by 4 if you have 4 occasions, and so forth. Then this part here, how far off your outcome is from what's predicted, that shows up here, meaning we're going to predict all of your outcomes from all of your predictors given the fixed effects. Here's V again, and then here's this thing, which is the same thing, meaning squared. So that's, it wraps around this V matrix essentially to create a squared term, sort of like how factor loadings get squared if you look at the notation for SEM. So point being, this is a formula. It is a recipe for creating height for each person's set of observations given the current guesses as to what your variance model parameters are. It goes through this and gives a combined height for each person. If we take the log of that, we can then add people's heights together rather than multiplying them. It's a trick to make the number more numerically stable. And then we can compare that total sum height to another set of guesses, right? Well, what if the random intercept was 10 instead of 9? Does that make the data taller or shorter? And it goes through this process of trying to find the tallest possible combination across people, and then it spits out that set of answers. And when we do model comparisons, we're trying to say, well, under this model, this is the tallest height I can get. If I add something, does it make it taller, right? Log likelihood is tall, is good. We take the -2 of that so that the -2 log likelihood difference is more easily computable. And that's why we have -2 log likelihood as lack of height, meaning smaller is better. But we're calculating all of these things. We're evaluating which parameters are relatively best using this particular formula. So when I say that your residuals are supposed to be normal, do you know why? Because we're using the normal distribution. That's like saying we're making the assumption that brownies have nuts. Well, did you put nuts in them? Then your brownies have nuts. What if you don't like nuts in your brownies? What might one do then? Not put nuts in? Pick a new recipe, right? Pick a new distribution. So all of the stuff that you hear about this being normal and that being normal, it's because that's the formula we're using to judge height. There are other distributions that we can use to judge height for other kinds of data, such as multivariate Bernoulli for binary outcomes. There's multivariate count ones for count type things. And there's a whole bunch of them that are out there. So then the log likelihood, after doing a little bit of algebra, on this formula looks like this. And this is the thing that you see in books. The process of how it figures out which set of values to try out next is way more complicated and not something that you need to lose sleep over. It uses calculus. The end. One byproduct of that, and I've highlighted this word because it's going to start showing up on some of the output, is gradient. That's the idea of the first derivative of the likelihood function with respect to that parameter. If you're really at the top of the mountain, if you think of a slope climbing a mountain here, it should be flat. So the close to zero you can get is an indicator that that parameter is being well estimated, that you really are at the best guess you can make given the data at hand. This number shows up in your output when you're using proc-glymics, when you have non-normal outcomes that you're analyzing, and it also can show up when we're using NL mixed, which is what we're going to do for heterogeneous variance models in the second half of this lecture. So then we go through and get the estimates. Second derivatives are used to get you the standard errors. And this is the part where I said fixed effects are calculated. Once you know what your best guess is for all of your random effect variances and covariances and all your residual variances and covariances, that formula there, it spits out the fixed effects from. So practically speaking, what that means is in these general models, fixed effects don't cause estimation problems. They don't have to get looked for in the same way that variances do. So if you want to break a model, add something random. Adding things that are fixed is not going to give you a problem. The only instance in which adding fixed effects I've seen break models is when the scale of it is problematic. So let's say that you're looking at an outcome or a predictor that's like number of dollars, like if you're predicting income or something. If you keep it in dollars, then the slope has to be like change in something per dollar. And then that slope can get tiny, 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 like 0.000 things, and SAS can't hang on to it, particularly if you try to give it a random slope. So that's the only instance in which I've seen fixed effects in general models cause problems. And you just change the scale and it should be okay in that case. Side note here, Remmel versus Emmel. Chapter 5 talks about this, but here's the two side by side again. Here's my height formula in Emmel. Here's my height formula in Remmel. They are identical up to this part right here. There's an extra part that gets subtracted off in Remmel that has to do with how well the fixed effects did. And that's why we can't compare -2 log likelihood AIC or BIC if we're using Remmel, because it's defining the likelihood function differently. Okay. So, big picture, the thing we're using to figure out which model parameters are best, are highest, assumes that they are normal because that's the formula we used. We can pick another formula if they're not. So then we get into checking for violations of model assumptions. And I had to stick this in the book even though I think it's kind of useless. I'll be quite honest. I think the appendix of chapter 7 is pretty useless, but I put it in because I had to. But there are some quotes here from another popular book, Singer and Willett, which was, I think, the industry standard for a number of years. I don't know if they've done a second edition, but it was 2003. And they have this thing, fitting a model with untenable assumptions is as senseless as fitting a model to data that are knowingly flawed. Well, agreed, right? However, how do you know if you've mastered all of the assumptions? How many of you ever just run one model and write it up and turn it in? Has that ever happened, Andrew? You're lying. No, we don't even have one model in our our effing homework, right? There's at least 4. So are you going to check all of the assumptions all of the time for everything? Well, no, they say maybe just, you know, the ones that make it into the final paper. Okay, well, that seems reasonable. Now, how do we check the assumptions? We prefer visual inspection. I tell you what, if my residual plot is going to stand in the way of my paper getting published, you better believe those things are fine. I visually inspected it and I thought it was fine. So the typical process of generating plots of residuals, I used to have a homework in this class a long, long time ago where I would deliberately mess up data and then I would give the students plots of the residuals and they had to figure out how I messed it up. It was impossible. It was impossible to generate a picture of residuals that was clear enough that we could all agree what the problem was. It was impossible. So I've soured on the idea of plotting things in terms of residuals in favor of finding ways to empirically test whether your model needs something else, because that will likely be more useful and reproducible. So depending on which side of the model then, violations have differential effects on your conclusions. Yes, sir. Yep. Mm-hmm. Nope. SAS does have that. It used to be that you could add the word residual on the model statement after the slash, and I think they may have changed it in 9.4. There's a plots option in ProcMix that you can ask for all those things. So yeah, it will spit out as much stuff as you want. When I was looking into this, my recollection is that those tests tend not to work very well, and so people don't put a whole lot of stock in them. So yeah, at the end of the day, I'm uncomfortable with staring at a picture and coming to a conclusion that I feel like I can defend when someone else might stare at the same picture and have a different response. So yeah, that's my take on it. But yes, you can do that in SAS. So in terms of ways to screw up a model, if you have the wrong fixed effects, then those are going to be biased. And if you have the wrong model for the variance, then the p-values and standard errors of your fixed effects are going to be off. So here then are the 3 types of assumptions here that you're familiar with: normality, constant variance, and one more. What are the magical 3? Normality, constant variance, and starts with an I. It's a big one. Independence, right? So let's talk about how all those things are still here in the stuff we're doing. And note general with asterisks by it, because the normal part is because we're using this multivariate normal formula to generate our likelihood. So normality of residuals, not outcomes, and independence and constant variance of residuals. Constant variance is my nicer way of saying homoscedasticity. How's that for a mouthful? Yes. And this is across sampling units and predictors, which is 2 different things here. So all of this still readily applies, except we have to think about it at each level, not just overall. Also, as an aside here, anytime you're using maximum likelihood, the regular flavor, or residual maximum likelihood, Remmel, we are assuming missing at random for outcomes. Missing at random is not testable. You just have to believe. It means it's conditionally random after taking into account the outcomes you do have for that person and the values on their predictors. So if you're concerned about missing data, the best thing you can do is put everything in the model you can think of that has to do with missing data. Reasons for attrition, reasons for selective not responding to items, anything like that. Anything you can put in should help. So here's some pictures. This is from the appendix of Chapter 7. So these are the types of plots you might see. Oh, I have skewed data, and then we have these QQ plot things. And these are the types of pictures here on the right-hand side that I used to have a homework assignment based off of. But this is an example of how residuals might indicate that there are particular problems. So what I did is generate just a single level model here where I have a predictor A, predictor B, and an interaction. So here is my random intercept. I guess it's a two-level model, excuse me. And here on the x-axis is A. And if I have all three of those fixed effects in as they were generated in the data, the residuals that you get should be flat and even. Flat meaning there's no trend that they grow or shrink as a function of A, and even meaning they're equally dispersed. There's not a point in the A variable at which the model works better or less better. So then these are three ways to screw this up. If on the top right here I omit the main effect of A, but I still fit the main effect of B and I fit their interaction, would I ever do this? No. But that what will happen is that you'll see the missing main effect of A here, which is positive, as a trend in the residuals that has not been modeled yet. If I forget the interaction term, that's this one that's flat, not even. The A by B interaction term means that what the slope of A should be is dictated by another variable. So in the middle of the distribution, it's okay, but it's way off on the ends because that's where a different slope would have been needed to create those different residuals. And if you forget everything, then you get this bottom picture here. So like I said, it was nearly impossible to generate pictures that were obviously wrong, that they would be sufficiently diagnostic. But you can generate these sorts of pictures in your software program of choice. One thing to keep in mind though, anytime you output a value for a random effect, that's known as an empirical Bayes estimate, they're going to be shrunken. They're not going to be what they would be in the model because they're going to be pushed to look more like the fixed effect as a function of having less data or having more aberrant data as well. So these y-axes are even a bit misleading. So the normal part then. In our general models here, we are saying that at level 1 within persons, our R matrix can be described by a multivariate normal distribution, and so we can decide what goes in it. So for instance, the R matrix that is a default in SAS and in most other programs, what is it? If you don't do anything, what do you get? Without a repeated statement where you change it, what do you get? Remember? I'll draw it for you. If you ask it to print it, the default R matrix looks like this. Same number on the diagonal, nothing on the off diagonals. What's that thing called? Not compound symmetry. Compound symmetry has the same on the diagonal and the same on the off diagonal, but it's not zero. VC, variance components, also independence is another one, or ID for identity. Depending on your software, that's what it's called. But that's the default R matrix. Because any relationship that we would have had across outcomes is supposed to be captured by G. However, we can test whether or not that R matrix that's VC is adequate, right? We can have heterogeneous variances by time, or we can add correlations among the residuals, topolitzes and autoregressives and all that stuff. The level 2 U's then have yet another multivariate normal distribution. So G, if you have a random intercept model, looks like this. If you add random slopes, a single random slope, it would look like this. And the U's have zero means with this estimated variance, covariance matrix in G. Now why can we say that the U's have a mean of 0? Fill in the blank here. Because the actual mean of the U is already in the model by some other name. It's the fixed effect. Do you remember how random is how far off you are. Random intercept is how far off your intercept is from the fixed intercept. Random slope is how far off your slope is from the fixed slope. So the fixed slope is the mean. That's why they have a mean of 0. And the random intercept and slope variances and their covariances get to be whatever they want by allowing type equals UN, unstructured. And that language, by the way, is universal across the packages that I know. Unstructured, that word. Is that the way what it's called in R? Do you know? Any R people? You don't know? Okay. All of the other ones have some kind of synonym structure that you have to learn, but unstructured seems to be the thing people have agreed on. So G should always be unstructured unless you're doing some sort of special trick to it that we haven't talked about yet. So what if then your residuals aren't likely to be normal? Like if you have a binary outcome. If you're predicting zeros and ones, are those ever going to have a normal distribution? No. Pick a new model. And so I am really hoping that we will get there this semester. We didn't last time, but this is where the idea of generalized models comes in. Pretty much everything that you've learned about general models is going to transfer to predicting models for other types of outcomes. It's just that you have the added complexity of a link function. So for instance, if I am predicting a binary longitudinal outcome, I'm going to do it likely through a logit link. Remember logits? Some of you do. What's a logit? Yeah, it's for binary. It's the, what's the definition of a logit? Some of you better know this. Yeah, the log of the odds of the probability of a 1. Yes, that's a logit. So you're doing the same multi-level modeling stuff, but you have to say predicted logit instead of predicted outcome. Or if you're doing count outcomes, the log, not the logit, the log gets used for those kinds of things. So in these models, I will note the random effects are always still assumed to be multivariate normal. These generalized models only change what happens at level 1, or the conditional distribution when you put it all back together again. There has been some recent work looking at whether or not if you have U's that are not normal, this is bad, and no one seems to care. So it looks like that may not be too big of a problem if that doesn't hold true, but the lack of options in software is going to be one big impediment to working around it. I will, as an aside here, talk about maximum likelihood. If you're going to work on these models on your own before we talk about them, different software packages have different defaults for estimation, and some of them only have the bad kind. So the last I heard, SPSS, for instance, only has the bad kind of maximum likelihood for these types of models. If you see in the description of it the words quasi or pseudo, do those words inspire confidence? No. Those are older methods of estimation that have fallen out of favor. They're fast, and that's why people still have them, but they don't work as well as true gold standard maximum likelihood. So you want to look for words like numeric integration, marginal maximum likelihood, or adaptive Gaussian quadrature. All of those words mean full flavor maximum likelihood, because then you can do -2 log likelihood tests the same way that we've been doing them, and you can have variance components that are accurately estimated. And by the way, there is no such thing as Remmel in these models. Remmel is only applicable to models with level 1 E's that are normal. Certain linear modeling textbooks talk about the idea of transforming data, right? You take your thing that's not normal and you log it, or you square root it. I can say root for that, right? Because I'm being dismissive. You square root it. There's only one time that I think those types of things are justified, and that is a log. It turns out that if you have data that are positively skewed. Wait, is it positive? The tail's this way. Is that positive? I always get this wrong. They look like this. Hump and then tail. Is that positive skew? Thank you. Yes, they look like that. A log works really nicely to reel in that tail, and if you log your outcome and then run proc mixed, you get the exact same likelihood as if you do it in Glimix and you tell it to use a log normal residual distribution instead. That's the one intersection of the two. Initiating system shutdown? No! Seriously?